Hello, my name is Krishna Narayanan. I am a professor in the Electrical and Computer Engineering Department at Texas A&M University, and I will be presenting the second part of this tutorial. What I would like to do in this part of the tutorial is to talk about three things. I would first like to talk about a mathematical formulation of the uncoordinated multiple axis and talk a little bit about the system model and what kind of metrics we are interested in. And then I would like to talk a little bit about information theoretic benchmarks that are relevant for this problem. And finally, I would like to very briefly review some things about how codes are typically designed for the Gaussian multiple access channel and why these codes cannot be directly used for the uncoordinated multiple access case. So let's start with the traditional Gaussian multiple access channel. This is a channel that has been studied in information theory for a very long time. It's typically discussed in textbooks. So in this channel, we have k users, and each user is assumed to have b bits of information or a b bit message. And each user encodes its information using a code book C into a code word X. Now, we assume that X satisfies a power constraint, or there is a constraint that the power of X has to be less than or equal to P. And all the K users transmit their code words. And what we observe at the receiver is the sum of all the transmitted code words. And there is Gaussian noise on top of that. And then there is a decoder at the receiver that tries to decode each of the individual messages. And we get an estimate of each message given by W1 hat through WK hat. And what we would like to do is to make sure that all the messages are decoded correctly. And typically, a metric that's used to assess the performance of the system or the scheme is the probability that at least one message is wrong, which we would call as the probability of error. Okay. Now, in classical or Gaussian multiple access channel or classical information theory, the number of users k is typically fixed. It's typically small. And what you do is you let n, which is the number of times you use the channel, to grow. And you want to be able to transmit proportionally more information. So you let n and b grow, and you ask yourself, what is the rate at which b can grow with n? Right? So that's classic information theory. And when we talk about the Gaussian multiple access channel, usually there are some assumptions that we don't explicitly talk about, but nevertheless, it's important for this talk. So usually what we assume is this. A user's information typically has the identity of the user as well as a payload or data that the user wishes to transmit. Normally, the payload is much, much longer than the identity part of the message. And it's typically assumed that there is a protocol, and somewhere in the higher layers of the protocol, the identity of the user is conveyed to the decoder. And typically, the user picks a code book or some kind of transmission resources that are dependent on this identity. For example, the code book that is chosen by each user will be maybe different, and it is chosen depending on the identity. And this is typically known to the decoder, right? Or maybe you choose time slots at which to transmit depending on the identity of the user, and the decoder knows when which user is transmitting. So typically there is an overhead for this. And in the first part of the tutorial, Dr. Chamberlain talked about all this. So this is an assumption in traditional Gaussian multiple access channels. And the assumption is that this overhead is small compared to the amount of payload that we have to transmit, right? Now, typically there is a capacity region for the multiple access scheme. So here is an example for two users. If you have two users, the two users can pick their rate to be row 1 and row 2, such that the rate has to fall within this pentagonal region, or any pair of rates within this pentagonal region is achievable. And the rates are given by rho 1 has to be smaller than 1/2 log 1 plus p over sigma squared, which this is assuming, or you can see that that is the rate that you can obtain if there is no interference from the other user at all. And the second part says that the sum of their rates cannot be any more than as though both users' powers is present at the same user. So, so this is half log 1 plus k times p over sigma squared, right? And if you think about how these things are proved, the proof is typically relies on choosing the code books at random. The code books are chosen to be random Gaussian code books. And the proof relies on the fact that if you pick any subset of the random variables x1 through xk and y, the asymptotic equipartition property holds for this. In other words, the empirical estimate of the mean of log of the joint probability is very close to that of the joint entropy. And this needs to be true for every subset of these random variables. And you can see that there is an exponentially large number of subsets of these random variables. However, this is not a big problem in traditional Gaussian multiple access case, because we fix k and we keep on increasing n. So in the limit as n becoming large, AEP holds for all these subsets of random variables. But you can see that the traditional Gaussian multiple access channel is not really a good model for machine-driven communication or the Internet of Things that we are interested in studying in this tutorial. For one, what we are typically interested in our case is large number of users, right? And in addition to it, we also have random access. So a better model for the machine-driven communication problem is to assume that you have a large number of users, and the number of users may actually grow with the block length. So this kind of a channel was studied by Chen, and Guo under the name of a many access channel with random user activity. So here, the idea is that there is a very large number of users, or the number of users is L sub n, and that grows with the number of times we use the channel. And each user is active with a certain probability given by alpha n. So the average number of users is alpha n times Ln, and this can grow as n grows. It's just that you don't want it to grow at a rate that is exponential with n. You will see why in the next slide, but still Ln can grow with n. And the idea is that, again, each user has two parts of the information. There is an identity part and a payload, and we need to identify both the identity and the payload together. Okay, so what Chen, and Guo were able to do is they computed the capacity of this channel, and they showed that the symmetric rate. So if you look at the rate, the point in the rate region where every user is transmitting at the same rate is given by this expression that I've shown here. We'll try to parse this expression now. So you can see that it's the max of 0 and a non-zero term, and the non-zero term has two parts. So first of all, this is the capacity in bits per user. So it's the total capacity over n channel users. So it says that the capacity, the first part of this what's inside the max has two terms. The first term, if you look at it, this is nothing but this is exactly the capacity of the kn user multiple access channel. This is the traditional Gaussian MAC capacity. But there is a penalty which is given by the second term here. And the penalty comes from the fact that we didn't assume that the user identities were already revealed to the decoder, and the users will have to somehow convey this information. And how much information do you have to convey to be able to resolve these identities? Well, if you think about it, each user is active with probability alpha n, and the total number of users is L sub n. right? So the total number of bits that you need to identify a subset of size alpha n times ln, or if each user is active with probability alpha n, the total number of bits that you need to identify this user is given by ln times the entropy function of alpha n. And when you normalize that by per user, you get the denominator k sub n. Okay, so indeed, the important part of Chen and Guo's result is that they were able to show that even though kn grows with n, unlike in the traditional Gaussian multiple access case, the proof can still be made to work. Okay, and and what this also shows is this: it shows that there is a small penalty in, okay, there is a capacity penalty because of the fact that we don't know the user identities. But depending on how quickly the number of users grows with n, the second term may be large or small. So for example, if ln is growing linearly with n, then the capacity penalty here, you can see it's a fixed penalty. So ln would be n times something, and then you get a small term here. Whereas if ln grows exponentially with n, then that's a problem because the second term may start to dominate, and then you get, you have to spend all your resources in trying to communicate your identity, and you don't have any resources to communicate your information. Okay. All right. So one more thing that's important about this is, this also sets the stage for saying we may want to think of schemes where you communicate your identity followed by something that you do to communicate your message. And indeed, Chen and Guo themselves propose such a scheme as a way to achieve the capacity expression that's given here. And you will see that this part of communicating the identities is typically going to involve a compressed sensing scheme. And this will be a running theme in the talk. Now, this still does not fully account for everything that we want to capture with the uncoordinated multiple access channel. Particularly, it does not capture two things. Particularly, it does not capture the fact that we are typically interested in sending small amounts of information. So the result by Chen and Guo is still an asymptotic result in n. But for most practical situations in machine-driven communication, so for example, there is a known IoT standard called the LoRaWAN, where here the typical numbers look like this. So each user typically is interested in sending only about 100 bits. So here, using asymptotic benchmarks from information theory like capacity do not necessarily give good insights or good benchmarks. And typically what you have here is, again, a system where you may have a very, very large number of total users. You may be thinking of 10,000s or millions of devices that are potentially that many of them in a geographic region that want to communicate. But at any given time, only a very small subset of them are active. So for example, in this standard, they look at the case when the number of active users may be from 25 to 300 active users. And typically, we may want to use the channel, roughly the order of like 30,000 times. So I think this is, of course, a specific example, but these numbers are good to keep in mind because I think it is good to have something concrete to be able to compare different schemes. Now, so this model was actually studied by Polyanskiy, and yeah, let me go here. So Yuri Polyanskiy studied this model, and he formulated the problem as follows. He said, okay, we have a very large number of users, out of which a small subset of them are active. And we have a finite number of bits and a finite number of channel users. And can we say something about what kind of error probabilities are achievable? And what he showed is that if you slightly change the metric that you are interested in, if you are, instead of asking for the probability of error in decoding the entire set of users, if you ask for the probability of error in decoding any particular user. Then he was able to derive a bound for the probability of error, and I'll talk about that in just a second. But before I go ahead and talk about this, I want to make sure we understand a few things about the formulation clearly. So again, each user has an identity part and a payload part that they want to transmit. Now, sometimes this identity part may or may not exist, but regardless, the amount of information can be thought of as having two parts. Now, if you think of this whole information together without separating the identity and the packet, then the decoder, what it really wants to do is this. The decoder only wants to get the set of all messages that were transmitted, right? It has this hat W1 hat to WK hat, and it doesn't really care about who transmitted what, because that identity is embedded in the message. So from a mathematical perspective, you can think of this problem as saying, K users transmitted something, and all I care about is getting the set of these messages. Okay, so this is what we mean by the decoding is done up to a permutation of the messages. And secondly, there is no coordination between the users. So what does that mean when there is no coordination between the users? The users cannot pick anything in their coding scheme that's dependent on their identity, or at least not explicitly. So what that means is every device has to employ the same encoding strategy. Okay, and as I've talked about before, we are interested in the case when you have a finite number of bits and we have a slightly different error metric. Now for this problem, okay, before I go there, a particular instance of this problem is what is called as the neighbor discovery problem. So if you consider the problem where you have a wireless network and a device wants to know the IP addresses of devices which are within a one hop neighborhood from this device. So one way to think about this problem is to say that, think of this multiple access problem that I just defined, where each user has no payload to transmit, but has only the identity of the user to transmit. And this problem is called the neighbor discovery problem. And you can see typically that the address space of for example, could be an IP address. It's typically like a 48-bit or a 64-bit IP address. So in this paper, Yuri Polyanskiy derived a bound on the probability of error, or what we call as an achievability bound. So the main result in this paper is the following theorem. So if you fix P prime, which is a power to be smaller than P, for any P prime smaller than P, there exists a code book with 2 to the B, M is 2 to the B, code words of length N, and a probability of error given by this expression is showed is achievable. Now, I didn't put the exact expression on the slide because the expression is pretty complicated, and there are 3 terms in the expression. There is a PT, QT, and a P0, and these expressions are given in Polyanskiy's paper. But the point of this is to say that he derived a bound on the achievable per user probability of error as a function of P, M, and N. I'm going to quickly walk you through the main idea in the proof. The idea is to use Gaussian random coding. So what you say is, I'm going to draw a code book. The code book has M code words, and each code word is drawn such that each element in the code word is a Gaussian random variable with 0 mean and variance P prime, where P prime is smaller than P. So let me try to move this, where P prime is smaller than P. And if you generate such code words, now there is a small, depending on how close P prime is to P, there is a probability that the power of the code word exceeds N times P. Now, if this happens, we will violate the power constraint. So we're not going to transmit those code words and instead just transmit 0. So this is basically what happens at the encoder. At the decoder observes Y, which is the output of the multiple access channel. And then the decoder exhaustively searches through all possible subsets of size k of indices, and it computes the Euclidean distance between y and the sum of sj's over those indices and picks the subset which has the smallest Euclidean distance. So this is, in other words, this is basically just a maximum likelihood decoder for the with the Gaussian random codebook. Now, clearly, the complexity of this is very, very large. So the complexity is exponentially large. And so this is not something that you can actually implement. And nevertheless, this gives you a achievability benchmark, right? And there is one parameter to optimize here, the p prime. Now, if you choose p prime to be too close to p, then the probability with which a user will violate the power constraint will be fairly large. However, if you make p prime to be fairly small, then you don't get enough protection against the noise. And so you want to trade off these two things, and therefore you have to optimize this p prime. And that's basically what he did in that paper. And to give you some visual insight into this bound, if you plot this bound such that you plot the required signal to noise ratio that you need to achieve a target probability of error. So I think here we fixed the probability of error to be like 5%. And then you see how the required signal to noise ratio grows with the number of active users. You get some plot like this. Now, you see that there are two distinct regions here. So there is one region where the number of active users is fairly small. In this region, you see that the slope of this curve is very, very shallow. So the required signal to noise ratio grows very weakly with the number of active users. And then there is nearly like a phase transition somewhere. And then beyond this, the required EB over a naught grows much more faster with K. Now, when the small K regime, more or less the performance is dominated due to the finite length or the finite block length, the fact that you have only 100 bits to transmit. Whereas in the second regime, in the large K regime, you're dominated by the fact that you have too much interference. Okay. And you will see this curve a few times in this tutorial again, because this is the benchmark that we are going to use to evaluate how good the codes that we design are. Okay, so the rest of the talk is really about trying to design codes that get close to this benchmark with a practical complexity. Okay, hopefully you caught on to the fact that while we can get this achievability bound, this is not something that you can actually implement in practice. And you should also keep in mind that this is an achievability scheme. So that's why I call this as a benchmark instead of any limit. Okay, now before we go on and talk about coding schemes that get close to the bound, I want to take a few minutes to convince you that things we know to do for the traditional Gaussian MAC may not be easy, or at least cannot be used directly for solving this problem, and or at least they will not give good designs to solve this problem. So let's take a quick look at how we typically achieve capacity or get close to capacity performance on the traditional Gaussian MAC. Now, what we know from several years of work in this area, and I'm not going to review this too much, is that the corner points in the multiple access region can be achieved using successive interference cancellation. So in other words, nothing more than single user codes and interference cancellation is required to be able to achieve these points. So for example, if you want to achieve this point, you would pick a rate for user 1, which is given by this value here, which is lower than the rate that you pick for user 2. You would pretend that user 2 is interference when you try to decode user 1. Once you've decoded user 1, you can subtract user 1 from y, and you can decode user 2 at a higher rate. And that will achieve the capacity at that corner point. Now, it's also known that any point along the dominant phase can be achieved with what is known as rate splitting, where the idea is each user can sort of think of themselves as multiple users and split the rates between the multiple streams. And again, only single user codes are required. But these kinds of solutions cannot work for the uncoordinated problem, because in these cases, you need to coordinate the rate selection between the users. So somebody has to tell one user to pick a lower rate and tell the other user to pick the higher rate. In the absence of such coordination, we are forced to work with the equal rate point in the MAC region. And typically, it's harder to design codes to get to that point. Particularly, you cannot just design single user codes to get to that point. And let's take a quick look at how we can get to this point without coordination. Let me make it very clear. The equal rate point is harder to get without coordination. Okay. So for example, there have been many advances in coding theory in the last several decades. And you might wonder, can you just take one of these codes and try to use it for this problem? So let's first understand why something like TDMA or CDMA will not work. So if you think about TDMA or FDMA, you need each person transmits in a different slot, and this is typically decided by the receiver, or it is coordinated. Without coordination, if you let users pick slots on their own, then they might collide with each other, and so this will not be an optimal solution. Now, what about orthogonal CDMA? Well, in CDMA, typically spreading sequences are assigned to users in a way that they are orthogonal to each other. And somebody has to do this spreading sequence assignment, right? And notice that in our case, we are interested in the total number of users being really large. And when the total number of users is really large, so for example, if you have, let's say 25 users are active, but you have 10,000 total users. Now, if you want to make sure that you can assign a fixed spreading sequence to each person in the network, then you have to use a spreading sequence length, which is 10,000, because you need a set of 10,000 sequences that are all orthogonal to each other. Now, if you do that, then you don't get enough dimensions for your coding. So in this case, then you get only 3 bits for your coding, but you have 100 bits to transmit. So clearly, this is not going to work. Another coding scheme that has been quite popular is interleave division multiple access. And in this case, what happens is each user encodes their information with a code book, or they choose the same code for all the users, but we use a different interleaver to interleave the coded outputs of each user. And then you can use an iterative decoder to do the decoding. And it has been shown that when the number of users is small and when the number of bits you have to transmit is reasonably large, this actually works quite well. But it's not been studied when we have very large number of users and when we have very short packets. That's one thing that has not been studied. And secondly, notice more importantly, that we need to know these interleavers. These interleavers have to be picked differently. Okay, somebody has to tell them what interleaver to pick, and this has to be known at the receiver. So again, some coordination is required. Another scheme that works well is spatially coupled LDPC codes. Now, in spatially coupled LDPC codes, we have some empirical results to show that if you have a 2-user multiple access channel, and if each user were to pick a spatially coupled LDPC code, but if they choose their graph according to 2 different permutations, then you can get fairly close to the equal rate point on the multiple access region here. Again, the drawbacks of this is that the 2 permutations that you choose have to be different, and they have to be known at the receiver. And also, spatially coupled codes are typically very good for very large block lengths, and they are not typically good for short block lengths, such as what we are interested in. And the last thing that I want to talk very briefly about is recently there has been results that show that polar codes can be used to achieve capacity of the multiple access channel. So for example, if you have a 2-user multiple access channel, what you can do is 2 users can pick 2 polar codes. So here I'm showing a polar transformation of length of size 4. And it turns out that if you use these 2 codes on a multiple access channel, then if you take any pair of indices from the two users. So it turns out that this channel with two inputs polarizes into one of 5 possible channels. Sometimes both these channels are bad channels, which means you don't want to transmit any information through those channels. Sometimes the second channel is good, but the first channel is bad. Sometimes the first channel is good, but the second channel is bad. Sometimes both channels are good. Now, in these cases, you know ahead of time where you can transmit information and where you should just use frozen bits. But there is a channel where it turns out that the sum capacity of the channel is 1, which means either user 1 can transmit and user 2 should use a frozen bit, or user 1 should use a frozen bit and user 2 should transmit information on this channel. But you don't know ahead of time who is going to use the frozen bit and who is going to transmit. So again, this requires some coordination between the two users to be able to allocate who is going to do what. And without that, this scheme will not work. So the recurrent theme, as you can see from here, or the main points I want to talk about is this. First of all, the traditional multiple access channel is not a good model for modeling what we want to do for machine-driven communication or IoT. The many access channel model deals somehow with the problem of number of users growing with n, but it doesn't deal with the finite block length nature. And Polyanskiy's result about the finite block length bound serves as a good benchmark against which we can compare our coding schemes. And finally, existing coding schemes are inherently assuming some form of coordination. Okay, this is something that's important to keep in mind. And so we cannot directly use them. Nevertheless, we're going to design many coding schemes which are all inspired by traditional coding schemes. You will see that some modifications to these coding schemes can be made to work well, can be made to account for the fact that we have an uncoordinated channel and we have a finite length. So for the rest of the talk, we're going to try to design coding schemes that get close to the finite block length benchmark that I talked about. And in particular, a recurrent theme is going to be to make connections between this unsourced multiple access channel and compressed sensing. You will see that in many of these schemes, there is an interplay between compressed sensing and multiple access channel, and advances in one field can advance the other, and that's going to be a recurrent theme in this talk. I'll see you back after a couple of more parts.